Okay. So we have the exam 3 review for Calc 2. So any questions? And just like immediately, if not, I can start on the first practice exam that you guys have. I'll wait a bit. Which problem specifically? Okay, so I think this subject or this exam is mostly on series, sequences, and Taylor series, right? So the first one I'd be looking at would be exam 3, prep quiz 1, which you should have access to on Canvas. And so this is just a determine whether a sequence converges or diverges are the 2 questions on here. Is that okay to start with for everybody? Okay. So this would be, so I'm just gonna exam 3, prep quiz 1. So this is just a single question with 2 parts, but it's just 2 separate sequences. So find if these converge or diverge. So A, we have A sub n is equal to 5 times 8 over 7, and then n minus 1. So we're checking the limit as n approaches infinity effectively. And you can either do, well, yeah, for this, so we have 8 over 7, which is a number greater than 1. And then, so this 5 doesn't really come into play too much. But since we have 8 over 7 to an nth power, as n increases, this is going to approach infinity. So the limit as n approaches infinity of 5 times 8 over 7 and minus 1, we get infinity. So this diverges. So again, so because this is n minus 1, we have 8 over 7 to the first. Well, if n equals 1, it'd be to the 0 at the start. And then we have 8 over 7 to the first. And from here we go 1 to 8 over 7, which is greater than 1. And 8 over 7 squared, which would be 64 over 49, which is greater than that. So we'll notice a trend like this. And since the numbers increase, goes to infinity, diverges. So B, we have A sub n is equal to, let's see, that's n squared plus n all over 2n cubed. So this one's a little trickier. Again, we're going to check for the limit as n approaches infinity. And for here, it helps if you remember your rules when you have polynomials in a quotient. So since we have 2n cubed on the bottom and only n squared on top, what ends up happening is this becomes insignificant compared to the bottom. And that's because whenever you have effectively for a quotient of polynomials, you just look at the highest power. And since we'd have n squared plus, oh, well, n squared over 2n cubed effectively, because that would become obsolete on the top. This would become obsolete on the bottom. We end up getting that effectively this is going to loosely equal 1 over 2n as n approaches infinity. And so the limit will be 0. So it'll approach. So this will approach 0. Because we'll have a larger number on the bottom always. So knowing that, we know that this converges. Any questions about this? If not, I can move on to the next bit. No questions? All right. I guess I can go on to exam 3 quiz 2. Again, if you ever want to go over a specific topic, feel free to stop me. I'm just going to kind of run through all the quizzes if nobody does. So let's see. Determine the sum of the first 11 terms of the following geometric series. Okay. All right. So for this, we got to use 2 equations. All right. So there are 2 equations for finding the sum of a geometric series. And so if we have this a and then r to the n minus 1, this will be okay. So for n equals 1 to infinity, I guess to n. So what we would have is this will be equal to a times 1 minus r to the n, and then all over 1 minus r. And this is only true if r does not equal 1 and the absolute value of r, or wait, oh wait, never mind. For this, we can use anything where r does not equal 1. So if we have the same one, but n equals infinity, then we get the equation this equation, a over 1 minus r. Okay. So after this, I'm going to go over Taylor and Mclaren series because someone asked a question about that, which is completely fair because that's the most recent topic, and that's what I figured most questions would be about. So this is only true if we have r is, well, the absolute value of r is less than 1. So given that, we have, let's see. Okay, so first we want to find sum of the first 11 numbers in this sequence. Or I guess it's a series. Yeah, it's a series. And it's a geometric series, which is the only way that this works. So we have, so this is infinity, but we're only finding the first 11 terms. N equals 1 of 2n over 7n minus 1. So what we can quickly do with this is say, so because we have to find an R and an A, what we can quickly do is we can find, or we can kind of do a distributive property here. So we can say that this, sorry about the ugly summation sign there, would be 2 over 7. And then if we do to the n minus 1, so both would be to the n minus 1. This is to the nth, so we'd have to multiply by 2. So that way this, so if we were to distribute that back in, we'd have 2 to the n minus 1 times 2, which becomes 2 to the n, and then 7 to the n minus 1 stays. So now we have our A and our R. So that's the little trick that you need to do for recognizing what A is. Or you can just find your first term by just plugging in n equals 1, and you get 2 anyways. So, but with this, we can then use this equation here. So we have A is equal to 2, 1 minus R is going to be 2/7. And this will be to the 11th power because we're doing 11 numbers. And then all over 1 minus R again. And now I don't really have a calculator on hand to do this. Yeah, A just does mean the first term, yeah. Okay. So yeah, I don't have a calculator to do this, but you just plug this in, get the answer that way. You might be able to, well, this you wouldn't want to do by hand. 11th power is not nice. I could give you 2 to the 11th power, it's 2048, yeah. But 7 to the 11th power, not fun. And then it's also not fun getting a direct answer for this. So then the next question, so number 2, we would have, so we're determining whether this sequence or series is convergent or divergent, and if it's convergent, we find the sum. So we have, oh, that's 5 to the negative n, I think. Yeah, we have 5 to the negative n times 2 to the n minus 1. So we can rewrite this, which I will do. Or actually, just keep it like that. And we start at n equals 1 and go to infinity. So this we can just say is equal to, I'm going to rewrite it in terms like that. We get 2 to the n minus 1 on top, and then 5 to the n on the bottom, which we can then rewrite as 2 over 5 to the n minus 1 times 1/5. So here we have our A, here we have our R. We notice that R is less than 1. And because this is a geometric series, we know that because R is less than 1, we have a convergent series. So from there, we can already find, so we already know it's convergent, so we can write that down. You could do the ratio test too, but because it's geometric, remember that R just has to be less than 1 in this case. So we can quickly use the equation up here, a over 1 minus r, and we get 1 over 5 over 1 minus 2/5. And this you can do by hand, because this is 1/5 over 3/5. 5's cancel, and we get, wait, did I do this right? Yeah, you get 1/3. So, any questions about that? Answer should be 2.799. Oh, for the top one, yeah. That seems about right. Because that would be, yeah, that seems right. So then, because someone asked about Taylor and Mclaren series, I will skip right to that. Because I'm assuming most of you probably have that down pat. So let me find a good one. Does anybody have an example from the prep quizzes? Prep quiz 6 might have it. That would be, yeah, this would cover it because this is 3rd degree Taylor polynomial. Okay, and that's with center at a equals 0. Yeah, okay. Ooh, this is a messy one. All right, so let's look at, so this is exam 3, prep quiz 6. For those of you that want to follow along. And this will be number 1. All right. So we have find T3, right? 3rd degree, yeah. T3 of x for f of x is equal to cosine of the square root of x. All right. So since it's t sub 3, we have to go to the 3rd derivative. We get, so f0 of x is obviously cosine square root of x. F prime, so that would be n equals 1. So the derivative of this, we have to use chain rule. Derivative of the inside would be, no wait, not negative. 1 over 2 square root of x. And then it would be sine. Oh wait, it would be negative because of the sine. Yep. Then we'd have f double prime. This is not the nice one. This would be, let's see. Wait, this is centered at x equals 0, isn't it? Or a equals 0. Which means you have to calculate it at a equal 0. So that's undefined. Am I doing this right? Oh, wait, I know what I did wrong. You don't want to do this. You want to do this for other problems. We want to do the cheap method. Right. Instead of having to deal with chain rule, we want to use our nice identities. So we already know for cosine, so cosine of x is going to equal all right, 1 minus, why is this? Why did they replace it with a? Okay. We want to do 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and then minus x to the 6th over 6 factorial. All right. And so what we can do is, so normally we'd know that this is f, or so f of x, or well, f of a, I should say. Following the equation, this would be reference of f double prime of a. And that's because we have f prime of a would be 0 because the first derivative is sine, and sine of 0 is 0. So we only need these two terms for our T3. And then because we have square root of x, if we substitute square root of x in here, all of our x's become the square root of x. And so we can shorthand this into 1 minus x over 2 factorial, which is 2. Does this make sense to everybody so far? Kinda. Let's see. Trying to think of a good way to describe it. So effectively what we're doing is, so our Taylor series, we can write out a bunch of expansions. So we know that cosine of x is equal to our 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and then minus yada, yada, yada. So this we can also write into a form n equals, do I want to start at 0? I think I just want to start at 0. To infinity, where we have, we have x to the 2n over n factorial. Oh wait, do I want to start at 0? Maybe I just, this is the tricky part. Do I want to start at 0 for this? I think I actually want to start at, oh wait, I know my problem. You do n equals 0, so this has to be 2n factorial. Yeah. Because then it goes 0 factorial is still 1. So you get that right. And then so on and so forth. So what we can do is, knowing this, if we have cosine of the square root of x, instead of going through all of the steps where we have to find f, or f of x, f prime, f double prime, what we can do is we can directly use these equations to substitute. If we have the square root of x, well, goes square root of x here, square root of x here, square root of x here, and then everything simplifies. Since it's the square root of x squared, it's x to the 1/2 squared. The rule for powers when you have a power to a power is you multiply. So 1/2 times 2 is 1. Yeah, okay. And so since it's 1, this simplifies to x, and that's why we get 1 minus x over 2. And then inside here, we would get x to the n, because it's 1/2 to the 2n. So 1/2 times 2n is just n. And then we still keep the 2n factorial here. Now the part of realizing where to stop this is understanding that cosine of x, we're skipping our odd primes or our odd derivatives. And that's because every odd derivative, we're back to sine. And so since we go cosine, sine, cosine, sine, these would be 0, these would be 1. And then because it switches, so cosine goes to negative sine stays at negative cosine. Then we go back to positive sine. So then we're looping back between negative and positive. And so then we can recognize that our first negative term is actually the third term in the Taylor series. Yeah. So going from here, we determine the third degree Taylor polynomial for a cosine squared of x centered at a equals 0. And because we already know that centered at a equals 0, we have this equation. If it wasn't this, we'd have an x minus a squared, x minus a to the 4th, so on and so forth up here. Plus, we'd also have to deal with the different derivative, which would be ugly, but because we don't have to deal with that, we can just keep this. So now we want to approximate. Okay. Yeah, we want to use our Taylor polynomial to approximate the integral of 0 to 2 cosine squared of x. And this is the tricky part, because for this, we're using, let's see. So use our Taylor, never mind, this isn't too tricky. So because we're using our T3 of x, that's the Taylor polynomial that we want. Sometimes they'd ask you to deal with this, and that would be much worse. But we want to take the integral of this. So we're going to approximate it using this. So we're going to integrate from 0 to 2, 1 minus x over 2 dx. So this is a straightforward integral. We just do, so integral of this is x. Integral of this would be x squared over 4. From 0 to 2, we get 2 minus 1, because it's 2 squared over 4. And then minus our 0 terms, which is just 0. And we get, oh, wait, did I do this wrong? Oh, I think the key is actually wrong on this one. Because if they have, so I don't know how many of you are looking at the key, but it has 1 minus x, or the integral of 1 minus x over 2, which we have right here. But then the next step, they have x, and then x cubed over 6, which I think we all know is wrong, right? Just increase the power by 1. So the answer should be 1 on the key, not 2/3, which they have. And that's because they accidentally added 2 powers to this. So just make a note of that. And if any of your buddies couldn't make it to these, make sure they know, in case they were scratching their heads at why they couldn't get the right answer. So yeah, answer should be 1 for this, for the approximation. And you could test this on a calculator. This isn't an easy integral to do by hand. So you want to test it on that. And then we have one last part for this question. We have, if we assume, so if we assume that n is equal to 1 over 100, on the interval from 0 to 2. 0 to 2. We are going to give a bound on the error using this approximation at x is equal to 2. All right. So we have our R2 of x hat. It's going to be equal to our m over n plus 1 factorial. I think technically, so it would be, yeah, and times x hat minus a to the n plus 1, or well, n plus 1. All right. So what we have is, we know our a is 0, so we can just ignore that. N is 2, and we can replace everything. So we have m is 1 over 100. N plus 1 factorial would be 3 factorial. So 3 times 2 times 1, which is 6. And then lastly, we have 2 to the n plus 1, which will be, why can't I think of it? No, 2 to the third, which is 8. So in the end, we get R2 of x hat is equal to 1 over 100 over 6 times 8. That reduces to 3. This becomes 4. And now we have 4 times, or so 4 times 1 over 100, which is 1 over 25. We can do a lot of simplification here. So that's 25. And we end up with 1 over 75. No, they have 4 over 300, which is the same thing. So we know that our estimate is going to be within 1 over 75 of the actual answer. You could test this on a calculator if you want to check. Should be relatively similar. Yeah. So that goes over kind of error bounds, Taylor series. Not really much on Mclaren series. Wait, this Mclaren is when a is not equal to 0, correct? You know that, Timothy? Is Mclaren a is not equal to 0, Taylor is a equals 0? Yeah, one or the other.
Taylor can be
Yeah.
Mclaren is depends on the function.
I always forget the vocab. I know the math, not the words. So any other questions about this? I think we covered a good range of topics on that, but we have plenty of time still. No questions? Okay, I guess I can look at another quiz. Let's see. So that was the last prep quiz. So let's look at quiz 5. See if that has some similar stuff. All right. Yeah, so this one's determine the Taylor series for the given function with center A by taking the derivatives and using the definition above. Ooh. All right. This is the hard stuff. Okay. So we have, so this will be prep quiz 5. So we have f of x is equal to 1 plus x and then all to the negative third. All right. And we have centered around a equals 0. Again, just it's nice when you have an a equals 0. But it doesn't change much when you have a not equal to 0. It just affects where you're starting and what you have to shift with. So first thing you want to do whenever you're finding a Taylor series is set up your derivatives. So for here, we need to determine an actual summation. So for this is a good rule of thumb. Always try to do at least the second derivative. If you need to, in order to find the pattern, take a third derivative, but it's not always necessary. And it really just depends on how good you are at recognizing patterns, which can be a little troublesome for some people. So first, find f prime. So you already know 1 plus x negative third. We also want to find f of a as well every time. So the derivative of this, we subtract 1 from the power. Typically, we'd have to deal with the chain rule, but because the derivative of the inside is 1, we don't have to deal with the chain rule. So we get negative 3, 1 plus x to negative 4. So this will be pretty straightforward going through. So f double prime will equal, so times negative 4. So positive 12, 1 plus x to negative 5. And then we keep going if we want to. I don't think we need to though. Possibly not. Maybe. It's weird how this goes. All right. Well, let's just stick with this, since I said typically you can do it with just the double derivative. So we know that our summation is going to equal f to the n, and this is the derivative of a, and then x minus a to the n all over n factorial. So if we put the first terms together, so we have f of a, or really f of 0, start with. So f of 0 is going to equal, so plug in 0 here, we get 1. We'll get 1 on the bottom every time, so we don't have to worry about it too much. F prime of 0 is going to be negative 3. And f double prime of 0 is going to equal 12. From there, if we do our little summation, we get, let's see, okay. So we'll start with 1 times x minus a to the, so we start at, this is technically 0, 1, 2. So we get, all right. So you start with 1 over 0 factorial, which is also 1. And then we do minus 3 over, or 3 times x minus 0 to the first. So it's 3x over 1 factorial, which is just a 1 again. And we do plus 12x squared. Again, doing that and that. Over, now we have 2 factorial, which will be just 2 here. And this isn't the easiest thing to start with, so maybe we want to go f triple prime real quick, which we then multiply this by 5, so we get 60. And then 1 plus x to the negative 6. Or negative 60, my bad. Minus 60 x cubed over, and now we have, so 0, 1, 2, 3 factorial, which will be 6. And so if I think this through, okay. So this we'll use a little bit of work from the fact that this is a power rule. So because we're multiplying first by -3, then by 4, well, we keep oscillating between negative and positive. So setting up our summation, because we can kind of start from here. So we have the summation, and we're going to start at, let's do n equals 0, since this is first the 0 term. Start at n equals 0, go to infinity. So first things first, we know that we oscillate between positive and negative. Since we start at positive, we're just going to do -1 to the n, because when n equals 0, this is positive, n equals 1, negative, positive, negative, positive, so on and so forth. Now, here comes the tricky part. Or well, I guess if you want the easy part first, it'd be x to the n next. And that's because we start at x to the 0 is 1, x to the first is x squared, well, x to the second is x squared, so on and so forth. So those are the give me's in this part, 3 points right there. Now comes the hard part. Here on the bottom, we have n factorial. So this is 0 factorial, 1 factorial, 2 factorial, 3 factorial. And now we'll notice on the top, we get 3 times 4. So we get 3 times 4, 3 times 5, or 3 times 4 times 5, I should say. And then we keep going. We multiply by 6 next. So 3 times 4 times 5 times 6. So where I'm going with this is we'll have effectively, we'll always have, so 1 factorial is just containing, well, obviously 1. And then up top, we have times 3. So you'd have to get rid of this 1. Well, I guess it's not the best to display it with that. I guess it'd be better to say, here we have 2 factorial. So this is 2 times 1, and then we have 3 times 4 up here. Wait, is that right? 2. Again, this is the wrong one to reference every time. I keep doing that. This is the right one to reference. So this one you do want to go to F triple prime. So here we have 3 times 2 times 1. Here we have 3 times 4 times 5. The 3 cancels. And then we're left with a 2. So we'll notice we have 2 times 3 times 4, or 2 on the bottom, and then 3 times 4 on top. So what we can reference from this is that we have, so 2 on the bottom is pretty consistent, except for here. The way that we deal with that is by looking here, we have 2 on the bottom again, and then we have, so this would be 3 factorial. We get n plus 1, because this is 4, so 3 plus 1 is 4, times n plus 2, which is, so 3 plus 2 is 5, and then all over 2, because we always have a 2 term. And that's because here, so we effectively have 3 factorial just without the 2 and the 1 here. Here we have 4 factorial, again, without the 2 and the 1, the 2's on the bottom. So on and so forth. So we have 5 factorial without the 2 and the 1. Of course, the 1 we can kind of ignore because it's just 1. Multiplying anything by 1 gives it itself. And so what ends up happening is we just always have these terms left over from the n factorial on the bottom, and then divide by 2 still. It's kind of a tricky one. But this is the answer on the key. And I think, do they go? Oh, they even go one further. I don't think I ever would have been able to recognize that pattern. It is a tricky pattern. Hopefully they don't give you anything as as messy as this in the quiz or in the exam, but they might. I doubt it though. Or actually, maybe. I don't know. I didn't take Calc 2 here. I don't know how hard the exams are. But I'm trying to think of any good tips to recognize this pattern. Some patterns are just, you need a lot of experience to recognize quickly. The best way is for power rules. Yeah, so for power rules specifically, you're often going to have something where your n factorial is going to cancel out in some manner. In this case, it cancels out in a very weird way because you have effectively an n factorial on the top just minus the 2 term. So what ends up happening is you just have 2 left on the bottom, and then you have your next 2 terms of where your n factorial would normally be, which sounds really weird when I say it, but that's just how it works out. So you get, so looking here, so we do our first couple of terms. The first term gives you next to nothing for information. The second term starts to give you something. You have that 3, but you're missing a 2 there. And that kind of comes in here. So once you look here, we see, okay, we have 3 times 4, and we have 2 factorial. So we have the next 2 terms of what the factorial is right there. And then here, again, we have 4 times 5. And we again have the next 2 terms of what the factorial is. Then everything, or we have our 3 cancel. If you were to go on to the next term, you'd have 3 times 4 times 5 times 6 all over 4 factorial. And again, this would be 4 times 3 times 2 times 1. So we notice that these cancel. Again, we have our next 2 terms. That's our n plus 1, n plus 2. And then we have the 2 left over. And that's how we find this. So for power terms, I really recommend writing out all the factors of the number and then trying to compare it to the n factorial. If you're scrunched on time, probably save these questions for last. Get your question or get your points on the easier ones and then come to this later because pattern recognition can take some time. Any questions about this problem? I know it was a real tricky one. Oh, and this is the final answer right here. I just had this box since that was the hard part. Just remember that if you find an oscillating pattern, add one of these in, make sure you start on the right sign and then you're set. And then make sure you get your X term because that's typically the next easiest one. And then anything that comes after that is the hard part. And I'd suggest trying some problem like that with either more power rules or maybe something completely different, like maybe a natural log turns into a power rule very quickly. But try it with some common functions that you might have to take multiple derivatives of. Like find in the book a example of this problem. Hopefully you have like a answer key to it in the back. But yeah. That will be like the hard question on your exam, probably one of these where you have to find the pattern. The error bounds, it just comes to knowing your equation and knowing how to find m, which will just be your maximum on the interval. But that can be a trick in itself. So if there aren't any questions, we can take like a little break and get ready for the 7 to 8 shift. Of course, we'll be well, two new coaches will be here teaching you guys. But if you don't have any questions and we're running low on time, I'll close it for now and it will be back up in like 5-7 minutes. Okay. Have a good rest of your day. And I'm going to stop recording.